Hello, this is work with Hyungrok, Shingo, Sato, and Junji Shikata. Let's first introduce some background about identity-based signature and Isogenies-based cryptography. Identity-based signature, or IBS, is a type of public key cryptography. In an identity-based signature, there is an authority called KGC having a master key pair and can issue a user secret key based on the user's identity. Then the user signs a message and the signature of verification can be done by using Alice's identity and master public key. This simplifies the process when mapping the the public key to the real-world identities. Isogenies-based cryptography is one of the potential post-quantum cryptography. The underlying hard problem is to compute a morphism which is usually called isogeny between two given supersingular elliptic curves over a finite field. There are two main sorts of isogeny-based key exchange protocols. One is SIDH and the other is C-side. SIDH has been completely broken last year by serious works as introduced just now, but C-side is still alive and has various applications. Here is the diagram of C-side, and in fact, C-side and the traditional Diffie-Hellman key exchange protocol are both instantiations of group action, hence their construction share some similarities. This work focuses on Isogeny-based IBS with tight security reduction. So we first give an overview of some related works. The signature scheme here are all based on C-side, and the latter IBS proposals are based on the previous signature schemes respectively. C-fish is the first efficient isogeny-based signature, and lossy C-fish provide tight security in the single user setting. There are some flaws in the security proof of IBS proposed by Penn and others. The security proof of shell and data, which we denote by SD, used ring technology, hence its security reduction is not tight. Here, tight security reduction means that when an adversary A breaks schemes S, is reduced to an adversary B solves problem P, the security loss error is a small constant. Our motivation of this research is that the security reduction of SD is not tight, and that although there is a generic approach to construct a tight security IBS by applying the certificate transformation to a signature scheme, which is tight security under the multi-user setting. And Penn and Wagner does present a way to construct such signature scheme from lattice and C-side, but the obtained IBS has limited efficiency. Our contribution includes the proposal of IBS with tight security reduction from the lossy fish, and the demonstration of the advantage of our proposal in terms of user secret key size and signature size. First, we give some preliminaries. An IBS consists of 4 algorithms. Setup algorithm takes a security parameter and output master key pair. The extract algorithm takes master key pair and the user's ID and output secret key for ID. Then signature signing algorithms using master pub key and user secret key to generate a signature for the pair of message M and ID. Finally, verification algorithm output accept or reject given master pub key ID, message M, and signature. For correctness, each correctly generated tuple master pub key ID, message M, and the corresponding signature should be verifiable. Then we introduce security definition of IBS. The usual security notion of IBS is unfortunability under chosen message attack or EUFCMA, which is defined by a security game between a challenger and an adversary. The challenger first generate a master key pair and send the master pub key to the adversary. Then the adversary is given 2 kinds of oracle, extract oracle and sign oracle. In extract oracle, inputting ID, a user secret key of ID is returned to the adversary. In sign oracle, a pair of ID and M is when a pair of ID and M is queried, a corresponding signature is returned to the adversary. Finally, if the adversary can generate verifiable tuple ID star, M star, and sigma star, then we say the adversary wins the game. And if the advantage for the for any polynomial time adversary to win the security game is negligible, we say the IBS is EUFCMA secure. There is another security mode called EUFCMA MK, which is matched with our proposal. The only difference between these 2 security modes is that in the EUFCMA MK security game, the adversary cannot query ID to the extract oracle if some pair of IDM has been queried to the sign oracle. Then we introduce C-side setting. As mentioned earlier, C-side setting, C-side is an instantiation of group action. Group action is a binary operation from G times X to X, which satisfies the identity and compatibility condition. Let G be the ideal class group of a quadratic order O, and X be the set of isomorphism classes of silver singular elite cups whose endomorphism ring over Fp is isomorphic to quadratic order O, then we get the C-side setting. Notice that each element in the ideal class group represents an isogeny, and to efficiently sample the element, elements of ideal class group, C-fish and lossy C-fish assumes that the ideal class group is cyclic and the generator G is known. But this assumption only holds at parameters C-side 512 by now. Next, our proposal is based on lossy C-fish. Lossy C-fish is constructed by applying the Fayette-Shamir transformation to an identification protocol. We first introduce base lossy C-fish identification protocol, and then lossy C-fish identification follows by enlarging the challenge space. The public parameter is the characteristic P, the generator G, and the order N of the ideal class group, and the starting elite class E0. Then consider the region R, where E10, E20 is two random elite class in X, and E11, E12 are connected with E10, E20 respectively by the isogeny GA. To prove the secret key of A, the prover randomly choose isogeny GR and compute commitment F1, F2, and send F1, F2 to the verifier. Then the verifier responds with challenge 0 or 1. According to the challenge, the prover response send the response R or R minus A to the verifier. Finally, the verifier can check isogeny G response is an isogeny between two proper elite class, which means according to the challenge, we can first determine two elite class, then we can check, the verifier can check if G response is the isogeny between connecting these two elite class. To enlarge the challenge space, the base lossy C-fish identification needs to be repeated T times simultaneously, which means we use T independent F1, F2 as a commitment. But this increase both sign time and signature size by a factor of T. So multi-public key is used to achieve a trade-off between public key size, sign time, and signature size. By using S public key, the challenge space becomes log S plus each times larger. So to achieve lambda-based security level, T log S plus each need to be larger than lambda. Then we present our proposal. We first build a base proposal from the base lossy C-fish, and then our proposal follows by enlarging the hash space of the base IBS. The setup algorithm is the same as the key generation of base lossy C-fish, which means we choose random B and C to generate E10, E20, and then choose random A to generate E11, E21, then set them as master public key and master secret key. The extract algorithm uses the master secret key to generate signature of the base lossy C-fish for ID, and then use them as a user secret key. Signing algorithm use the response in the user secret key to generate signature of the base lossy C-fish for the pair of message M and ID. Then return this signature and the commitment F1, F2 as the signature of IBS. Finally, the verifier can recovers the challenge according to F1, F2, and ID. Then, according to the challenge and the challenge dash, we can verify that the G response dash is an isogeny between two proper elite cars. And to enlarge the hash space, a similar method as lossy C-fish is used to are used, which means we use the S1 and S0 and the T1 in the extractor algorithm to enlarge the hash space of H, and T2 S1 in the sign algorithm to enlarge the hash space of H dash. And to achieve lambda-based security level, these two inequalities need to be satisfied. Then we give a comparison between our scheme and the existing IBS. From this table, we see that our IBS, our scheme achieves the tightest security bound. This is because PW used the certificate transformation, and the security of PW is reduced to two independent hard problems, but the security of our proposal is reduced only to one hard problem. Then we compare the user secret key size and signature size under the 128-bit security level. This parameter table T1, T2, S0, S1 is chosen according to the optimized setting of pen and others. This is because the underlying signature of pen and others, which is C sign, share some similarity with lossy C-fish, and our framework of IBS is same. From this table, we see that when S1 is chosen to be small, the user secret key size and the signature size of our scheme are much smaller than PW. But if S1 is chosen to be large, then the user secret key size of our scheme is still favorable, but our signature size becomes 2 times larger than PW. Finally, we give our conclusion. In this work, we proposed tightly secure IBS from the lossy C-fish, and we show that if S1 is chosen properly, then the secret key size and the signature size for our IBS are smaller than PW. For future work, there are still some controversies about quantum security of C side. So if in order to achieve some expected quantum security, we may need to compute the structure of a larger ideal class group, and this may be achieved by the technology used in the Scallop. And we may also consider to construct IBS from other isogeny-based signature schemes, such as SkiSign introduced just now. But since SkiSign is built from a particular starting elite class, the approach in this work cannot be applied directly to the SkiSign. Thank you for listening.
So thank you very much. Do we have any questions? We have 2 microphones right there and right there. All right, while people are thinking, I'll go ahead and ask a question. And I think, this one. I think you can also use that if you would like, but don't stand too close to this one or it'll go.
No?
Yeah, maybe stand right there though so they don't. Yeah. So you all used the unforgeability under chosen message attack with the MK. You may have said this and I may have missed it. Was that because it's stronger or was that just needed for your proof?
It is just the need for your purse because it is for better simulation in the security proof. And yes, it is weaker than the standard security notion of UFCMA. I think.
Perfect, thank you. All right, do we have any other questions? And I think there's somebody that's keeping an eye on Zoom, and I think that there are no questions there. All right, let's go ahead and thank our speaker again.